Thank you so much.
Put this, and then this one you can point on any screen.
I think the pointer seems working.
Yeah, I mean. Okay, is this okay for you?
I think most of the time I will just click.
Yeah.
Thank you so much.
Okay, let's get started. Today we are very happy to invite Minshuo Chen as our colloquium speaker. Minshuo Chen is an assistant professor with the Department of Industrial Engineering and Management Science at Northwestern University. He was an associate research scholar with the Department of ECE at Princeton University, and he completed his PhD study from the School of SYE in Georgia Tech. His research focuses on developing principled methodologies and theoretical foundations of deep learning with a particular interest in generative models, including diffusion models, foundations of machine learning such as optimization and sample efficiency, and reinforcement learning. Okay, now without further ado, let's give the stage to Minshuo. Thank you.
Thank you for having me. Thank you for inviting me. This great campus, beautiful sceneries, very similar to Northwestern, although I think here the number of lakes wings, and in Northwestern the size of the lake wings a little bit. And thank you for this very kind suite here. So what I'm talking about today is generalization of diffusion models, and typically understanding generalization of diffusion models. Of course, there may be some not familiar words to you, like what are diffusion models, and maybe generalization. You can think of, okay, I train a model, then I deploy the model on some unseen tasks, then the model is expected to perform well, then this is called a generalization. Okay, so the particular context of understanding generalization today will be unstructured data, and also a very annoying phenomenon observed in many of the generative models, which is memorization. So memorization basically says, okay, you are not providing new things, but just to reproduce what you have seen in the training data set. So I don't think I need to convince you that generative AI is revolutionize your maybe daily lives or even PhD courses, because sometimes you can ask generative AIs to do homeworks for you, right? Although I'm not recommending that. By the way, so these two figures are just created by me with interactions with the ChatGPT-5. So the first figure is created when I was using ChatGPT-5 on the Mid-Autumn Festival. I just type in that prompt, can you generate a Mobius ring that's under the moon? And this is type of the figure that the ChatGPT-5 generated. And then I moved to the second figure, which is I saying, okay, can you generate a similar style figure that gives us an impression of what memorization looks like? So the model generates this type of kind of like a really brownish brain, and inside that brain it appears some like a very fancy structure. Okay, so there's no denying that generative AI has been very capable of doing many fancy stuff that people can hardly imagine like 5 years ago. And the generative AI's emergence actually marked this shift from a discriminative AI to generative AI. And previously in discriminative AI, what we are doing is we try to assign labels or estimate some responses based on some input. And this input can be some type of label data that I want to characterize those images into different categories, dogs or cats. And the model is trained by taking those label data, and the output of the model is just some descriptive information of your input. Like this is a dog, this is a cat. Of course, this type of research has been started very early, even dates back to 1970s or 1960s when neural networks first appeared as a statistical model. And in the beginning of this century, people are still doing research in this direction, particularly in the first 10 years of this century. And after that, there's a paradigm shift where nowadays people are more familiar with the name like foundation models. So foundation models are just created by taking massive training data, and those massive training data can be taken from different domains, and they have different modalities. Foundation models are just try to capture what are some intrinsic properties of those data instead of seeking any type of labels. You don't see any type of descriptive information underneath those data. And after that, this is the deployment phase of a foundation model. Now we feed in these models with some like labeled data or instructions. So this large foundation model is first trained, I will say, unsupervised on some large corpus of data set. And then it will be detailed or fine-tuned towards some of very high-level or specific tasks. Like, can you respond to my prompt? Can you help me classify something? Of course, it can reproduce the old functioning of deep learning. So we were mainly talking about this paradigm, talking about generative models. So a more concrete understanding of generative models are this generative model is to generate new things. And how they generate new things, they start with some pure noise, and then they try to transform this noise into the data. On the training side, we take image, audio, different modalities of the data into the system, and then we expect that the output will mimic important characteristics of your training data. Of course, we don't want to make the generated image exactly the same as your training data. That's not of interest of us. So I will try to distinguish the large generative models using these two phases. The first phase is the modeling phase. And this typically happens in the training stage. We have large collection of data points, and then we want to find what are the underlying distribution of your data. So here P bracket dot means the underlying distribution of your data. And often, sometimes we are caring about conditional distributions, like what is the distribution of your dogs? Then this Y is just a label of dogs or labels of cats. So we can kind of like try to categorize our training data into different categories, and we try to model what is the underlying distribution. The second stage is sampling. So after learning or modeling the data, we want to generate new things. So this is just a sampling from our learned distribution. So we can generate 1x, we can generate more x's, of course, if we have like computational resources. So there's kind of like no limit of how we use these trained models, because we can use it repeatedly to generate new things. So if I instantiate this paradigm, the modeling and the sampling procedures into language generation, then we see that on the modeling side, we are using some model called autoregressive model. Autoregressive model just try to predict the next word given its previous words. Then if we can compete this process for different words, then we can try to model a whole sentence or even a whole passage of languages. And when we try to sampling from these language models, we again do this autoregressive sampling. So we generate the first word first, and then the second conditioned on the first, the third conditioned on the first two words, and then we complete a sentence. And finally, we can complete a passage, even longer books. I have to regret to tell you, language models is not the focus of today's talk. We were talking about diffusion models. Well, diffusion models is kind of like a different methodologies, which is very different from language modeling, because here on the modeling side, I put a word diffusion. So diffusion basically means we are gradually lose our track of the original data. How can we lose the track of the original data? We can add noises to that. Don't worry too much about what diffusion means, because we will revisit a little bit in the later introduction. On the sampling side, we are doing denoising. So you can think of denoising as the reverse process of diffusion, because in diffusion, we're adding noise, and the denoising basically means we are removing noise to generate new things. And here, this denoising is depicted by this animation. We see that we start from a pure noise. So this is a noise sampled from a Gaussian distribution. And then we gradually make that corgi log appear. So it's kind of like a black magic. How can we possibly generate things from a pure noise? And this is something that we will also introduce a little bit later. Well, this slide is actually prepared when I was preparing for a job talk, and I'm talking about diffusion models. And at that time, I think this slide is quite neatly organized because we have like very neat results, and the number of results is also kind of like limited. But nowadays, I think this slide is more like a Jamboard right now. So starting from the very beginning, diffusion models has beat against image generation. It achieved the record-breaking performances. And later, people are trying to use these diffusion models in larger data set, and you can see that out of 8 leading models, 8 leading models, there are 6 models using diffusions. Apart from purely like computer vision applications, audio generations, language generations, and even like video generations are also making a diffusion models as their backbone model. And the people are using it in like very like heated discussions. So Stability.ai is actually a startup company, and I think there's a report saying that in the past 3 months, but not starting from here, but I think in year 2022, in 3 months' time, they raised over $10 million, and the company only has like 13 people in that. Well, I think at that time, the slide stops here. But moving forward, we have more results, like generative AI image new protein structures. So it's kind of like diffusion models are making success in the biochemical and the biomolecular simulation regimes. It can also make reinforcement learning systems better, helps you with robotic controls and mechanical arms. And there are also more fancy styles, like you can change your photorealistic portrait of yourself or other people. And if you're a game lover, then diffusion models is a must try. So it can be your like a game engine. And I think successful examples, including it can construct like real things when you do like a first-person shooting games like CS. And now diffusion models are kind of like try to share some successes with the large language models. Diffusion models are also successful in language generations. Previously, people are thinking that, okay, diffusion models might be only successful in domains that's different from language, like computer vision and all other like different application domains. However, people have proved that diffusion models can also be very successful in language generation. They have higher speed compared to autoregressive models. However, the sheer performance in many of the reasoning tasks are still not on par with the autoregressive language models. Therefore, this is kind of like the recent active research direction of diffusion generative models. I hope I have convinced you that the success of diffusion models is quite like astonishing, and it can be successful in many of the cross domains. However, there are actually many of the mysteries happening why diffusion models are this successful. So the first mystery comes from the high dimensionality of your data. Just imagine I want to generate an image. The resolution of the image can be really, really high, like 1,024 pixels times 1,024 pixels for a very high resolution image. There's a classical result that says, if I want to model this type of high dimensional data, and I'm only allow some type of error epsilon, then the underneath neural network should of this type of size. Okay, this looks a little bit like abstract. How does this bound tells you? Let's try to instantiate this to the ImageNet data set. The image there has a dimension 224 times 224 times 3. So 3 is for RGB channels. So if we instantiate that epsilon to be like 10%, so 10% is just a mediocre accuracy for nowadays applications, then the network size should be this large, 10 to the power of 224 times 224. Well, I can spend a whole year of writing out the number of zeros if I want to calculate what exactly this number is. But what in reality is, diffusion models they have a neural network inside these models. And the number of parameters in the models is, although very large, like 5 billion parameters, but if you compare 5 billion with that 10 to the power of 224 times 224, you will see that the diffusion model is kind of like a tiny or almost like a size 0 model compared to that huge number. And the number of samples used to train diffusion models are kind of like 500 billion, or like even some type of like smaller than this 500 billion samples. And if we want to compare this 500 billion samples to that very large exponential, it's almost equal to 0. So the first mystery kind of like showing that due to the curse of dimensionality, because of that large exponent, why we expect the diffusion models can be that successful in generating real-looking images or other high-dimensional applications. The second mystery, well, let's just forget about the curse of dimensionality and accept that diffusion models are powerful, but it is still powerful up to some extent. On the left, we see that we have a training data that that is an image of a famous woman. And we try to generate, using this prompt, living in the light with Graham lots. Then we can generate like a different image, but those generated samples are almost the same compared to the training data. It says, okay, the well-trained diffusion model is even not generating new things. It's limiting its creativity, and in some like high-stake and sensitive applications, this can create many of the privacy and the data safety concerns. On the right-hand side, this is much better. So we have an initial training data that's being the Bernese mountain dog, and then we generate different figures. They share very similar characteristics of Bernese dogs. However, they look quite differently. So this is a very good case of diffusion models can generalize. But on the right-hand side, this is worrisome. But how these memorization happens? So in this talk, we will try to demystify these two mysteries of the success of diffusion models. But before that, I will introduce what is diffusion models, because this might seem a little bit like alien to you. And for the fourth part, I will just try to briefly mention one application or one use case of diffusion models for very important applications. So I will try to make this presentation interactive, so feel free to stop me if you have any questions. Okay, any questions? All right, perfect. So this is a more detailed breakdown of how diffusion models generate samples. Let me bring up this like enlarged demonstration of how diffusion models generate samples. We start from pure noise. Then we make the corgi dog gradually appear. So you can already understand that generative diffusion models are generating things in a sequential manner, not like starting directly from the noise and then we magically end up with the real data or real looking data. Therefore, underneath this generation process, there are actually two coupled processes. That's we have briefly mentioned, like one is the diffusion process and one is the denoising process. So understand how we generate noise and then we end up with a real looking image is kind of like really complicated, but we can start with something simpler. And that simpler is the diffusion process. And we also call it a forward process, which says we start with a data distribution, then we want to transform the data distribution into the noise. So let me emphasize why we want to study this process. Because if imagine, so we have a time machine and we can transport back in time. Therefore, if we can we can make this forward process possible, then we travel back in time will give us the transformation from noise to data. But let me just pause for this like very intuitive understanding of how we generate the data points, but try to elaborate how we can make our data distribution into a pure Gaussian noise. So the idea of transforming our data distribution into noise is not that complicated because we can do two things simultaneously. The first thing is we can always shrink the magnitude of our data point, which is like those blue dots in the bottom row. And the second thing is we are adding larger and larger Gaussian noises to each of the data point, which is shown as the blue shaded area around each solid blue dots. If we continue this process for sufficiently long time, then the end of the day we get each of the data point will be suppressed in the manifold, in the magnitude. Therefore, the magnitude of the data point will be almost zero. And at the same time, we are adding larger and larger variances, Gaussian noises, into each of the data point. So the end of the day, we get a almost perfect Gaussian distribution. Okay? Anyone have any questions about this? Yes. Yes, and the shrinkage speed is really fast. It's exponential shrinkage.
And then you have a T, I'm sorry, you have a T, so because you're doing this sequentially over time.
Yes, yes. So I'm choosing this continuous time formulation, but in practice, we will need some like a discretization to describe the interval 0 to capital T into different pieces. But you are like 100% correct that at each step of the transformation, we are adding Gaussian noise and also shrink the magnitude of the data. Yeah. Okay.
So using the diffusion model. So I'm a queuing theory, so I think of diffusion.
Yeah, diffusion model is a very old concept in the queuing theory, and I think maybe the more accurate description of diffusion model nowadays for this application is diffusion generative model. Other questions? Okay, cool. Now this is the fancy part. So again, imagine that we have a time machine that we can transform back in time. We can travel back in time. Then this travel back in time exactly gives us the transformation from the noise to the data distribution. However, the tricky part is what is the time machine here? Why this is possible? So this result dates back to 1986, where people try to establish that a forward or OU process can have a backward process. And the difference of that backward process to the forward process is this added drift term. And this drift term is our time machine. So in the diffusion generative models, this has a name, score function. More precisely, this is Stein's score function. And inside the score function, we have several notations. First, what is this small p? So in the previous slide, we see that the data distribution will be gradually transformed into noise, and this small p is actually the marginal distribution of your data at time t. Okay? So in the backward process, we are gradually putting this PT information back into our noise distribution. And this is kind of like the intuitive understanding why diffusion models can generate your data from pure noise. It is driven by this score function, and the score function consists of your data information. Unfortunately, this score function is unknown to us because it consists of your data distribution. Therefore, this is the learning part of the diffusion models. So first of all, the correspondence between the forward and the backward processes they are matching at the corresponding times at their marginal distributions. So the starting point of the forward process is almost the distribution of the end of the backward process, and the end of the forward process is almost the starting point of the backward process. And here I want to emphasize that this is not saying that, okay, I give you an image and then I add noise to it. I transform this into a noise. Then I can recover the original image. So this is not telling something like this. This is called like image blurring, or kind of like a reconstruction of your noisy image. Diffusion model making the correspondence or match of the forward and the backward process in the distributional sense. So this is just saying that at the corresponding times, the distribution is the same, not saying that we can reproduce samples. Okay, so we don't know what is our time machine, therefore we need to learn it. And a golden practice in implementation is use this like very fancy looking network architecture. And this is called UNet because people can arrange it in a letter U format. Therefore, people call it UNet. Okay, there's nothing fancy about that. And in fact, this is just a convolutional residual neural network. So I want to dive deep into how to train a diffusion model because the loss function will look something like this one. It involves the integration over time because we need to dictate how we transform for every time. And inside this integration, we have a kind of like a least square problem. The least square problem is making S the parameterized of the score function. And this S is actually a representation of that nicely looking U neural network. And this training loss is actually not implementable because what we don't know is this target quantity gradient of log PT. Therefore, there's a bunch of implementation tricks so that this loss function can finally be implementable. Okay. All right. Are there any questions? Yes.
I have a question that like the picture of the dog, you are estimating the distribution of the dog, and actually your data set is like approximate the true distribution of the dog in the world. Mm-hmm. So have we considered this gap, or just treat the data set as a true distribution?
Well, so this is a very good question, and this is also relevant to the memorization. Because we don't know the ground truth distribution of the dogs, and the only information we have are the collected real images. Therefore, the hope is we can learn from our collected data useful informations about the ground truth distribution. Okay. Other questions?
So for every time step, the architecture of the score function is the same for UNet, right?
Yes. So the architecture of the function is always the same. However, you can see that the architecture will take two inputs. One is your noisy state, and the other one is time.
So the architecture will not change with respect to the time step?
No. Other questions? Okay. So now let's try to understand our first mystery, why diffusion models are that successful for really high-dimensional applications. There's one common belief that practical data sets, although they appear to be high-dimensional, but intrinsically they are low-dimensional. And this is a figure from a photographer that's taking photos of the same teapot on the table. You will see that these images can be of really high resolution, but the composition of the image is quite simple. There's only one object, and then the yellowish background, the supporting part is a table, and sometimes people are just like forgetting about that supporting table. So you can imagine the free parameters governing this set of images is quite low compared to the number of pixels in the image. People try to estimate what are the intrinsic dimensionalities of the data set, and this estimation is really striking because the ambient dimension, or the number of pixels, is 224 times 224 times 3, but the estimated intrinsic dimension is no more than 43. I won't say this 43 is a very accurate estimation of the intrinsic dimensionality. It can be slightly higher, it can still be lower, but this actually gives you the impression that practical data sets are intrinsically simple instead of they are looking really scary on their ambient dimensionality. So what we try to do is we can model this observation as a manifold hypothesis. What we do is we say that our data sets are concentrated on a low-dimensional manifold embedded in a high-dimensional space. Here, notation convention, capital D is the ambient dimension, and the small d is the intrinsic dimension. And what is a manifold? You can think of a manifold as a mixture of local neighborhoods, and each local neighborhood is intrinsically simple, can be transformed into a low-dimensional Euclidean space. Okay. Well, in fact, neural networks are adaptive to those type of data structures. This is like no a fancy message here. In regression tasks, in classification tasks, in reinforcement learning, those like descriptive machine learning tasks, people have shown that neural networks are adaptive. So adaptive means the number of parameters of the network don't need to scale with the ambient dimensionality, but they only need to scale with the intrinsic dimensionality. And the other thing is also the same. For sample complexities, we only need to pay a sample complexity dependent on the intrinsic dimensionality instead of the ambient dimensionality. So this is already a very, very, very significant improvement to explain the gap between the statistical or applied math theoretical understandings with the success of the applications. However, in terms of understanding diffusion models, these results are far from enough. The reason is those tasks, regression, classification, reinforcement learning, are still kind of like 10 years ago things that's coming from the first paradigm of machine learning or artificial intelligence. But let me be more precise. What limits us to understand the diffusion models? First of all, diffusion models are not generating in one step. It introduces a dynamical evolution of your noise into your data. Therefore, to understand why diffusion models are successful, we need to keep track of the dynamic. So it's kind of like the additional time index creates us a lot of trouble here. The second thing, which is more like inherent to diffusion models, because we start with noise does not have any intrinsic structures. So you can imagine that in the noisy process, we start with something really high structured, and then we add noise to it, then we gradually lose the structure. In the backward process, we need to reproduce this structure. So this whole process is kind of like you are using a self-driving Tesla, and you are putting full confidence in the autopilot system of the Tesla, expecting that it will land you in the correct destination. However, why? And the real challenging here is, how does the diffusion models effectively reduce your exploration of the whole space finally into your designated destination, which is a low-dimensional manifold? So to understand these two challenges, let's start with something simple. Suppose our data is a linear subspace data. So our data can be represented as x equal to a times z. A is a tall matrix here because we try to make our intrinsic dimensions low. So dimension of A is capital D times small d. And this matrix is unknown to us. If we know the matrix A, then there's nothing special here. We can just do the data transformation and learn it from the low dimensional space. We also make some simplification to that really fancy looking U network architecture. We put some like encoder and decoder, and then in between the encoder and the decoder, it's some like a fully connected neural network. This is almost a U-net because this encoder and the decoder are of projection and dimension lifting purposes. The encoder will project your high-dimensional data into a low-dimensional space, and that decoder will lift your low-dimensional data into the original high-dimensional space. It is very similar to the U-net, although U-net uses a nonlinear transformation, and it also gradually changes your input dimension. So under these two simplifications, we can show the following. Remember, score function is our time machine, right? And this time, I'm telling you that this time machine composes two components. One component tells you how you evolve in the subspace direction, and the other machine tells you how can you move towards your final destination. In more science flavor, the first part is the on-subspace score function, and the second part is called the orthogonal score function. If you remember that here matrix A is unknown to us, and if we try to make the simplification assumption that A has orthonormal columns, then identity minus AA transpose is a projection operator. And it is orthogonal to the on-subspace score function because on-subspace score function is on the subspace of the linear subspace. So looking at the equation might be a little bit like overwhelming. So let me do some animation. Suppose I have a subspace here. This is our final destination. At the time t1, I'm here. away from the subspace, not on the subspace, of course. Then the movement of this point, the movement actually means the evolution of this point because we are trying to simulate the backward process and reproduce our data points. It's decomposed into two parts. The first part is the blue arrow, which is dictated by the on-subspace score function, which tells you the projection point of this xt1 will move towards a certain direction so that eventually it will meet the distribution on the subspace. There's a second movement, which is that orange arrow. It says, okay, your movement of your point will monotonically towards that subspace. You cannot escape, you cannot moving far away from that subspace because of that orthogonal score. At a later time, xt2, you see that I'm closer to our final destination. And the interesting thing here is we are still subjected to some movement inside the subspace, but the attraction from the subspace to this point x2 is larger compared to the attraction of the subspace to point xt1. The reason being that if t is small, we can see that orthogonal score has a leading factor 1 divided by 1 minus e to the power of minus t. And if t approaches 0, this term is almost infinite. Okay? So it's kind of like saying the closer you are to the subspace as time evolves, the more you cannot escape from that subspace. So it's kind of like creating some black hole effect. If you are close to that black hole, you will be attracted to that black hole, and you cannot escape. Therefore, finally, we can have this very large attraction to the subspace, and eventually we can generate a sample point on the subspace. Okay? So this is a very important decomposition because now we don't need to care about the whole dimensional trajectory. We only need to care about on the subspace, what are our projection point evolves. And this is a very effective dimension reduction because we now reduce our dynamics in the full space to the dynamics in the intrinsic linear subspace. Okay? So building upon this insight, we can establish this theorem. Although I think this convergence rate is not that important here, but the important observation from this convergence rate is it has a dependence on the intrinsic dimension instead of the capital D dimension. If you still remember, in the mystery 1, we have an exponential dependent on capital D. Here we only have small d here. So the takeaway message of this theorem is diffusion models are accurate in learning distributions because it can converge as sample size increases. It does not suffer from the curse of dimensionality, and it is adaptive to the data intrinsic structures because we can even say more that the subspace is also learned accurately. Okay? Are there questions? Yeah, we know small d. Yeah, yeah, we assume that we know small d. Well, A is unknown, and A will be estimated when we train the diffusion model, and this is why diffusion models are adaptive. Well, this is a very good point. I will generalize this theorem to nonlinear models. So this is kind of like give you an intuitive flavor of why diffusion models are capable of reproducing intrinsically low-dimensional structures. So we can move from this subspace simplification to the real, generic and smooth manifold settings. So remember, in the subspace case, we are decompose our score into two components. One is the on-subspace score, and one is the orthogonal. And here, orthogonal is indeed orthogonal to the on-subspace score function. Now on the right-hand side, we have this type of little bit banded over smooth manifold. And here we see that in the left-hand side, this projection point can be globally defined because subspace is a global structure. But for manifold, it's kind of like we're only capable of defining some local projection points. Because manifold intuitively consists of different local regions, and the geometry in different local regions can be very different from each other. Therefore, although we can establish a very similar result to decompose the score into the unmanifold and the orthogonal score, but the caveat here is they are not orthogonal anymore. There are actually some interactions between your different local neighborhoods on the manifold. And it is not always true that the point will move in directly orthogonally towards the subspace here in the manifold case. So there is a little bit more complicated insights of the decomposition. So now the decomposition actually does not happen globally. We need to do two-stage decomposition. The first stage is the point xt is far away from the manifold. And in this case, we are actually viewing the manifold as a combination of tangent spaces. So you can think of this as we are developing some linear or piecewise linear approximation to the manifold. And on each of the linear subspace, we can do some type of decomposition close to the linear subspace case we have. Therefore, now we see that manifold is a mixture, and we have the first one is the tangent subspace score, and the second one is some type of projection to that tangent space. So as time evolves, now we are at time xt2. So this point moves supposedly to be closer to the manifold, and then we can define some like local decomposition. Why it is local? Because this xt2 point is close to the manifold. It is less likely that this point will be finally placed towards a very far away point on the manifold. Therefore, we only need to care about some like local regions on the manifold. Therefore, we can remove that mixture, but only care about some like a local neighborhood on the manifold that's close to our point. And another thing is, here xt2 can have a unique projection point on the manifold because of the distance between xt2 and the manifold is relatively small. Okay? Of course, this existence of the projection will depend on the curvature or the geometry of the manifold. So here, the first part, I call it local charge score, and the second part is, again, some type of direction that's moving towards the manifold. So a little bit like technical exposure, however, the carry message is in the large noise situation, we are developing some piecewise linear approximation to the manifold. And in the small noise region, we are doing some local decomposition as if the manifold is restricted into a small subset. Using this result, we can establish this convergence result. Now the convergence is again dependent on the dimension of the manifold, small d. But we have another term that's poly tau, and the tau is a curvature. So intuitively speaking, if I have a really zigzaggy manifold, then the learning is, of course, more difficult compared to I have a very smooth manifold. Okay. So the additional take-home message for this generalization to manifold is we see that diffusion models now are fully adaptive to very non-smooth low-dimensional structures. And this result is actually min-max optimal in special cases, regardless of the dependence on the curvature. And the other thing is it is adaptive to the manifold curvature. Okay. Are there questions?
So how do you know it's close enough so we can switch to the other
Yeah, so in practice, this switching is actually happening automatically because the network is adaptive to the manifold structure when we try to do the learning. And this separation is kind of like motivated by the theoretical practical observations, and we can develop this theoretical threshold. So in the theory, the separation between the large noise and the small noise is the existence of the unique projection of your noisy point to the manifold. If that unique projection exists, then it indicates that the small noise decomposition comes into play. Yes?
What is the definition of HT?
Oh, Yeah, so I'm kind of like lazy to explain those like notations. So HT is actually the variance of the noise added to the original data. So this is determined by your forward process. You can think of this as a time-dependent but a deterministic quantity. So in the subspace case, we have ht being 1 minus e to the minus t, and here I am just lazy to write that equation to make this equation a little bit nicer. Okay. Other questions? Oh, how much time I have? Okay. So I think I will be really quick about like the memorization and the generalization stuff. So in fact, establishing some like convergence in the distribution is not that informative about whether we are memorizing data or not. So here is a perfect example. On the left, we have a very nicely looking estimation of the ground truth. So the ground truth is a solid line, and the estimation is a broken line. On the right, we have kind of like a very spotty estimation of the ground truth. But the bad news is, if we want to evaluate the Wasserstein distance between the two distributions, they are equal. Of course, memorization happens when we have the second type of thing, because second type of distribution is hyperphatically constructed from some samples of the ground truth distribution. Then how can we distinguish that diffusion models are learning the first one instead of the second one? And the second one is prone to memorization because it put emphasis on each of the samples from the ground truth distribution. We can look at the different properties of the score function. The first one has a really nicely looking score function. It is zigzagging a little bit, and the magnitude of the score is well controlled. But if we look at the second score function of the empirical or this generated distribution, we can see that the score function is now highly zigzagging, and the magnitude is 15 times larger than the very nicely looking ground truth score function. There's a very nice separation result in neural network approximations saying that in order to approximate a very complicated and zigzagging score function, we need to pay a lot of efforts. So you can see already from the size of the two figures, the second one is a much fat structure compared to the first one. And the first one can approximate the ground truth score, but the second one can approximate the empirical score. The size of the network will grow with respect to the sample size n for the empirical score, but this is not true for the ground truth. So the bottom line here is, in order to approximate or learn the score function, the network can have very compact representation instead of learning the empirical score functions. And of course, learning the empirical score function will lead to the memorization, reproducing your training data. Therefore, we use this motivation to, maybe I can skip this type of like simulation result, but try to do some like plug and play pruning methodologies. So most of the time, memorization happens when your score neural network is too large, because large networks has large capacities, and it can potentially approximate or learn the empirical score function. Therefore, we need to prevent this thing from happening. So here is an example of using diffusion transformers. There are different attention heads. Then the goal here is we may prune some unimportant attention heads. However, these attention heads might be responsible for reproducing your original training samples. How we do that is, in the first step, we will identify what are the least contributing attention heads. We can compute some scores, like 0.96 for the first one, but the third one is very low in the contribution score. Although I won't tell you the details of how can we compute those attention scores. Then in the second step, we will prune those attention heads to limit the expressiveness. And this is basically saying that we just eliminate the third attention head. To make the model perform well, we can retrain a little bit on the remaining two heads. Here I give you some examples. The first row of the images are the original model and the nearest neighbor in the training data set. We see that those images are very similar before we do the pruning. And on the bottom row, it's the result of after performing the pruning, we can see that the generated images of the pruned model is kind of like have larger variabilities compared to the training data. Of course, for the dogs and the planes are still very similar, but for the horses, we generate really like new things, and those images are quite of high quality. So bear me with saying high quality because this is CIFAR 10 data set. The image resolution is 32 times 32. So I don't think I have the full time to discuss one interesting application of diffusion models, which is kind of like, up to now, we are only talking about generation under no conditions. But in most of the cases, we are generating things with some conditions. And this condition can be like your input prompt for generating images. And in other applications, this condition can be your biochemical properties, or in manufacturing applications, it can be many requirements or hard constraints. Therefore, we want to generate samples in those situations obeying those constraints. So the novel idea here is we can formulate this as a generative optimization problem. So the objective function is your constraints or meetness or satisfactory level of your constraints. Then what you want to do is to generate some samples that can maximize or satisfy this constraint. So the new idea here is instead of doing a trajectory-based optimization of some like objective function, we are directly sample from some trained distribution instead of looking for some trajectories. Okay? And this is making full usage of the power of diffusion models because they can be very accurate and adaptive to learning what is this distribution. So for the sake of time, I think I will just restrict the discussion of this part for some like offline discussions. So thank you everyone for the questions and for your attention.
Okay, any questions? I have a question. So in your talk for using a diffusion model, when the real data is really of a low dimensional, then you are going from a pretty sharp image to the noise. I just wonder, is it possible for us to start from somewhere in the middle? Let's say our data is somehow polluted of some random noise, which is quite common in lots of application area, and go either way, either to sharpen that to the image with or data with more information related to the variation that we care about, or to generate more data by taking consideration the existing noise inside it.
Yeah. So this is a fantastic question. So first of all, there are two directions that we can pursue. Number one is we start with noisy image, and then we still want to train a good performing diffusion model. So this is highly possible because if your noise is limited to some extent, then the training of diffusion model can automatically remove some of the noise because you already played with the noise. Although this is not guaranteed, so I won't say this is like a theoretical guaranteed. However, in many of the real applications, people have shown that adding noise even performs better results because adding noise to your very clean data kind of like smooths your original data distribution. And the second thing is, suppose I have a trained model, and then I give you a noisy image. Can you produce some clean version of that? And this is called some purification of the noise. And this is also very capable when we use a very well-trained diffusion models. What we try to do is we can estimate what is the noise magnitude. This can be very coarse estimation. Then we can try to find what are the corresponding time of t that adds a comparable amount of noise to your clean data. Then we can just directly start at that point to backward the process to generate some clean image. So this is called like purification.
Okay. Thank you so much. Any questions?
Thank you very much. I learned a lot. I have a question about how important it is, or how the methods in practice move from like the Brownian, the continuous time sort of representation of this process, and then actually like implement it. How important is it to determine the right time step? Are these things determined dynamically, or what happens if you get like your time stepping wrong in this sort of?
Well, I will say in most of the current implementations, this discretization is not very sensitive, or the performance is not that sensitive to the discretization. And there are mainly two time schedules, so two the like discretization methods. Number one is using the exponential integrator, so which says we first sample uniformly of the time, and then we raise it to the exponential and use that time to do the discretization of the backward process. This is almost the go-to choice for many of the cross-domain applications. And there's one other sophisticated scheme, which is called the EDM scheme of the noise scheduling. It is based on some like a second-order approximation to the noise. But overall, I think regardless how you choose the two, the performance won't change significantly, and it is pretty robust to your noise scheduling.
Yeah, I have another question. So in your in your talk, you basically focus more on the understanding of the diffusion process and how it converges to this underlying low dimensional manifold structure. Yes. I just wonder, is it possible to have some mechanism for the model to actually use this kind of approach, this kind of analytical thinking to understand the structure of this manifold? For example, is it possible for this manifold to be, the product of two lower dimensional, set, etc.?
Yeah. So I think this is also a very interesting idea, and people already have done some work in this direction, which is, so it's kind of like a little bit like implied in the analysis. So because the score decomposes, we can extract useful components from the score neural network as an estimation of the underlying data manifold. And there are papers and recent research to try to use this type of method to estimate what is the curvature of your underlying data geometry and what is the sometimes even intrinsic dimensionality of your data.
Yeah, thank you so much for your answering. Now let's give the speaker another round of applause, and thank you so much. diffusion 这种东西，它要是用在那个，就比如说之前咱们早点说。